Okay, that is a single layer perceptron. Of course, there's a limitation in single layer perceptron. Is that you will find later if the data set consists of a complex relation of non-linear relation there, the capability of single layer perceptron in solving that problem is very poor. That is why they introduced to another architecture which is also known as a multi-layer perceptron. So what is the meaning by multi-layer perceptrons? Meaning that instead of you have, this is still output layer, the layer which is the final layer before you produce the output there. Of course, this should be head there. Okay, the final layer before you can, because before the system can produce the Y head there, is still known as a output layer. Okay, this is your output layer, and then instead of directly from the input to the output layer, the multi-layer perceptron is when you introduce the layer, the middle layer, which is known as a hidden layer. So hidden layer is the layer between the input and the output layer. So remember, in some, I already mentioned to you, some textbook they call this one as our input layer. So even the input layer is not count as a layer, because we talk about a single layer perceptron is actually even you have input layer and output layer, the one that consists of neuron is the output layer, so that's why they call it single layer perceptron. Now we talk about multi-layer perceptron because now you have more than two layer consists of neuron. One is output layer, another more than one layer consists of output consists of neuron. So one is output layer which consists of neuron, and then one is output layer which consists of output neuron, and another one is hidden layer which consists of also as consists of several neurons there. So why they call it multi-layer? Okay, this is the simplest example of multi-layer perceptron. You only have the output layer, and then the other layer is hidden layer, and then this one is the input layer. So meanings that the hidden layer is the simplest one. You have only one hidden layer, but you still can have more and more hidden layer. Here means that it's not just single hidden layer. If you talk about two hidden layer, three hidden layer, is also known as a multi-layer perceptron. So that's why they call it multi-layer perceptron. So you have an n layer processing and numbers of layer processing. The difference is just the last layer should be output layer, the first layer should be input layer. Why and the input layer is not count there, because of the one that consists of neuron is just the hidden layer and the output layer. Or in this slide they call it an intermediate layer. Intermediate layer is the hidden layer. Okay, this is several type of multi-layer perceptron. You can see here is also known as a two-layer neural network. Again, why two? Because this is one, this is two. This is not counted because this one don't have any neurons there. This one will consist of neuron, or they call it a one hidden layer neural network. In some textbook they call it one hidden layer neural network, means that you only have one hidden layer. Of course, if you talk about one hidden layer, means that it should also have a output layer. It should, because the last layer that the final layer should be output layer. It should not be something else. You need to have an output layer that is the medium to transfer the data from the hidden layer to the final output. So that's why they call it the output layer. Okay, this is the example of 3 layer in n, 1, 2, 3, or 2 hidden layer and n, 1, 2. So you can have more and more like that. Okay, as for multi-layer perceptron can be used to overcome data that cannot be separated only by using single layer. So again, like I discussed before, this is the the cases there. Okay, this is a non-linear. Of course, by using a single layer perceptron, which is of course this one is represented by input function and output function, and if you combine together, it's look like logistic regression. If you assume the f is sigmoid function, this is what you can produce: a single linear hyperplane or single linear line that represent the boundary that separate between the blue point and the gray points. So of course, if you want to tackle these cases, this one is incapable to do that, because the limitation, this function is only can represent this single lines there. So which is why, if you introduce the hidden layer like this, okay, this one is a single layer perceptron. Now you have a multi-layer perceptron. Then you will see that if you talk about, still this is a binary classification, but for logistic, for this one, which is equivalent to logistic regression, you are incapable to tackle this problem. So that is why, in order to tackle this one, you need two lines or two boundary, linear boundary. By introduced with the multi-layer, which is you have two neuron at the, okay, of course this is remember, this one is your hidden layer, okay, hidden layer, and this one is your output layer. So by introduce you with the hidden layers there, then this point there might be combination of this point and cascade with this point, it generate this one. The combination of this point and this point generate that point. So now, even this one is a binary classifier, it can tackle this this kind of cases where you need to have more than one linear or straight line boundary. You need to have that to tackle that. So that is the why people try to introduce with the hidden layer. So imagine that if you introduce more and more numbers of hidden layer, it can solve many complicated cases as compared to the logistic regression itself, because remember that why, like I said before, a single neuron, this logistic regression is can be represented by a single unit of neuron. Imagine if I cascade a million or several set of logistic regression together, it can generate a complicated function which can solve a complicated cases if you have that kind of problem or that kind of data set. Okay, now we talk about what is the effects when you have a big numbers. What happened actually when you have increased the layer number and the layer size? What actually happened? What is the effect? What is what is the beneficial you get there? Okay, if you are increasing the size and the numbers, you are also increase the capacity of the neural network. Means that the capacity or the capability of your neural network in solving complicated data set or in generating a complicated function it's going towards better and better. Okay, meaning that it doesn't matter any complicated cases. If you come out with more neurons, more number of layer and more bigger number or bigger size of network, we can solve complicated cases. But the trade-off is that, okay, it can learn to classify more complicated cases. That is the advantage of increasing the number of neuron or increasing the size of the neuron. Now the capability of classifier in solving complicated cases is better and better, but the disadvantage is that more likely to overfit the data train. Meaning that's why if you have a small data, for example, your data is not too big, like let's say just 100 samples, but let's say the neuron is also the number of neuron 100, so it's not it's not suitable to do that. That is because the overfit will happen, meaning that you generate a border to separate between many classes in strict way, and then of course during the training process you get high accuracy, while if you test on the unseen data you get very poor result, or it's mean by the you have a high training accuracy but you have a poor testing accuracy. That is condition that condition happen when you are training when that condition happen, meaning that the training data is higher and the testing data is lower, then that is what we call as a overfitting. Okay, so that's why people try to tune around how much what is the optimum size to tackle your problem, because different problem have different size of networks. It depend on how much data and how complicated the data, the relation between the input and output. Then that's why people, when design the artificial neural network, they try to tune what is the best size for that problem. So it depend on, if you try to vary the size of hidden layer, try to vary the size of neuron, if you find out the training data is higher but the testing data is lower, or in this case later I will show to you, instead of testing data we have another data known as a validation data. So because the testing data is to test the final performance, but to avoid the overfitting happen, we can use the method where you training by using if you find out when you training using the training data and you find out the accuracy is higher, and when you test the same model with validation data and the accuracy of validation the validation accuracy is lower, that is where the overfitting happens. So to avoid that, normally I think in MATLAB as well, when they do some training, they always to double check with the validation accuracy. If they find out the validation if the training accuracy is going up and the validation accuracy going down, then it will stop the iteration, because if they continue to iterate that one, the overfitting will happen. So that is the complicated that is one of the stopping criteria that we don't discuss in our syllabus, but during the assignment you need to understand that, then you know what happened is actually, because again I think even in the previous lecture we just give you some mechanism in how to do some stop iteration during the iteration, but one of it is that using in MATLAB is that once you find out your training accuracy is going high, but at the same time the validation accuracy is going down, then the iteration is stopped. That is a stop criteria in MATLAB algorithm, because now because your training process is not going towards converts, but it's also check whether the overfitting condition happen or not. If the overfitting condition happen, then you must stop the iteration. Okay, that is the effect. This is another effects of if you introduce several number of hidden neurons, means that this one is still one single meanings that you have okay, what's the meaning by that is that you still have 3 layer there. One is the input layer, hidden layer, and output layer, but we just vary how many neurons there inside this hidden layer. The first one is 3, so this 3, so this one is 6, means that there's a 6 there. 1 2 3 there's a 1 2 3 4 5 6. This one 20, means there's a 20 neurons inside this hidden neuron. So by increasing the size of or number of neuron inside this hidden neuron, this is happen. As you can see that this is managed to classify between the red and the red and the green zone, but of course there's a red points there, there's several red points there, is still at the green region. So by increasing the number of neurons there, you will find out now, for example, by increasing into 6, then you can touch this one, means that you manage to cover, this should be a red here. Of course, if you increase into 20, what will happen? So now it's will much better there, means that you can reach at this point. Again, imagine if you increase more and more, what will happen? So now this border will become so strict and very rigid. It might be something like this. Okay, sometimes it can be up into this one. If you increase the neuron, so the border can be something like this. Okay, it's very strict in decision making, means that it's too strict in okay. This is where actually the overfitting happen. Okay, once your border is too strict or too strict on the training data set. Sorry, I forget to cover this one as well. It should be something like that. Yep. Okay, so when you increase the hidden neuron more and more, and the border now shrink into very small and strict according to the given training data. So now what happened is that if you measure the training accuracy, of course in this case you get 100% accuracy, training accuracy. But let's say I give some data which is not used for training, I call it a validation data. I give that data, it's a unseen data. It might be here, that red, let's say the red point there is there, or the red point is there. So this is a example of validation data. Once you apply the validation data, then you calculate the validation accuracy, you will get poor accuracies there. That once you find out you have a poor accuracy on validation side but high accuracy on training side, that is where the overfitting happen. Means that if you imagine in data set is the border is very strict, fit into training data without any tolerance, tolerance there. So that's why if you test on validation data, which is might be a little close to this one, it should be there. But for actual case, this one should be red also. But because your border already shrink into training data, that's why you get the test accuracy or the validation accuracy is very small, or is very poor as compared to training accuracy. So that's why there's a trade-off there. Increasing the size, if the data is not enough, you have a small data, but you try to find the best function to represent that training data, and the neural network can provide you with that excellent function that can draw the border of your training data. But of course the trade-off that you have go towards the overfitting, where you have a poor in terms of testing data. Means that the unseen data, when you test, you get poor accuracy because your border is very strict in decision as compared to this condition, this one or this one or this one, where the hidden layer is only 20, where is still a tolerance there to accept some point which is close to this point. So it's a very tolerance as compared to this one, which is the overfitting. There's a strict lines there. So in other words, that is what happen if you are increasing the layer number and the size there. Okay, by using only single layer perceptron, it works like your logistic regression. If you have this kind of condition where the data is linearly separable, but your data is non-linearly separable like this, of course this one line here represented by one neuron. You need to have multiple neuron to represent, to combine or cascade together, then you can generate the border or the border that in this shape of these polygons there, because you have 1 2 3 4 5. You must have at least 5 neuron to do that. And then of course, if you talk about more non-linear crystals like this, let's say it's a still binary, but now the regions there is not just single line that is merged together, but you need another separate line that merged together. To do that, which is can have a capability to classify between white dot and black dot, then you need to introduce with hidden layer and more hidden layer, because the more hidden layer you have, the more boundary region you can have. If you only have a single layer perceptron with multiple neuron, you still have the capability to generate multiple line, but it's a connected and a closed loop lines like this. And of course, only by depending on single neuron, you can only generate only a single line. Okay, I repeat, single neuron, because of this logistic regression, you only have a single line. Single layer, but you just increasing this one is not single layer, it is a 2 layer. As some 2 layer neural network, you can have a closed loop, because this one, because you have a multiple neuron. That's why the combination of this many equation will produce a multiple line like this. But if you have this kind of data where you need more and more closed loop border, then you need to increase more and more layer, because the more layer hidden layer you added at the center there, then you can represent with, it can be represented with many single layer like this.